Hello everyone, welcome to Robotics 2. This is going to be the fourth method of solving this problem for the velocity of point I, of this single arm manipulator, where you simply have this one joint rotating theta, and it's with reference to the inertial reference frame out here, which is this distance, and then this distance, so on and so forth. Hopefully you've watched the other videos so you know how to do that. This time we're going to do it with quaternions. So set up the basic equation here. The velocity of I is equal to the velocity, or B dot, velocity of frame B basically, plus ITB, transformation matrix, dotted, times the vector from B to I in reference to B. So if we do this into quaternions has four specific parameters, 3 for the rotation and 1 for the angle of rotation. So the axis will be rotating about, in this case, since it's around z. U is going to equal 1. Hopefully you've been introduced to quaternions. I'm not going to do the introduction here in this video. I'm basically just going to work through this problem. And then theta is going to be equal to theta. The angle, so this is the angle of rotation, and this is the axis of rotation that that angle occurs about. And basically you have your quaternion, which is going to be equal to theta 0, 0, 1. And that's your quaternion, if you want to set it up like that, if that's how you've seen it before. So now we're going to put this, since we only have theta really, we're going to solve this quaternion in reference to Euler angles. So we're going to set this up, Q. If you've seen the standard quaternion matrix, this will be a little bit clearer. Again, I'm not able to show you that, so it's going to be not as easy if you haven't seen quaternions before. I'll try to do an intro video as soon as possible. 0, 0, sine of theta over 2, which is equal to Q naught 0, 0, Q3. This is how you set up a quaternion. This has to be a unit quaternion, and the way you do that, to prove that, is Q0 squared plus Q3 squared is equal to 1. That's the only way you can use a quaternion in order to find angular velocity or to really use it as anything. You can only use a unit quaternion, and the only way it's a unit quaternion is to take the magnitude of it, which is what this equation is. So this is basically a constraint that we can use to help solve this equation out. So ITB in terms of quaternions is going to be equal to Q naught squared minus Q3 squared minus 2 Q naught Q3 0, 0, 2 Q naught Q3 Q naught squared minus Q3 squared 1, 0, 0. This is a quaternion representation of a rotation about z, and you can kind of see this, how this would work out. Q naught minus Q3, so on and so forth. It's Q symmetric matrix, so on and so forth. If you've seen the quaternion, here, let me see if I can pull up the quaternion matrix for you. That'll make this a little bit clearer. Okay, so the quaternion matrix can be seen right here. This is where we got U and theta, basically. We will eventually do these calculations coming up. And then this is the quaternion matrix, where you have Q naught, Q1, Q2, Q3, so on and so forth. This is where we just created ITB for this last problem, is from this matrix by filling out the values that we had available based on the initial setup. So pause this video, write this down so you can look at it, and then I'm going to keep on going with the example. So over here, Q naught, we realize that we only have cosine of theta over 2 because this is a standard setup for it. And let me see if I can show you the equation here for that. When you're setting up a quaternion, you use basically this equation. This is how you transfer a quaternion into Euler angles. You use this equation basically right here, which is where the cosine theta over 2 comes from and the sine theta over 2 comes from. And since we have no forward magnitude, there's nothing out here in front except a 1. This is equal to Q0 and Q3. You have a unit quaternion. You sub that into the quaternion matrix, and you're able to get out the ITB that you want. Okay, so now, continuing to solve this. Gotta get back to my notes here for this problem, make sure I don't confuse you guys any more than I hope haven't already. Alright, so ITB dot then, because in order to do that we have to get ITB dot based on this equation up here. ITB dot is equal to, taking the derivative of all this stuff, is 2q naught q dot, which is a product rule and a power rule, minus 2q3 q3 dot minus 2q naught dot q3 minus 2q naught q3 dot 0 0 0, and then we have 2q naught dot q3 plus 2q naught q3 dot 2q naught q naught dot minus 2q3 q3 dot 0 0 0. Extend that back down, and there you go. And that's your ITB dot with quaternions. It's a little bit, some people get a little bit confused with the differentiation here, but hopefully it's not too bad. With this situation, you just take the derivative of q naught, brings down the 2 q naught, and then you take the derivative of basically the inside, then you consider q naught the inside since it's quaternion, and you end up with q naught dot. And then you go ahead and do this thing again over here with the q3, do the same kind of deal over here, so on and so forth. So you basically consider q naught as a function, a quaternion as a function, that you take the derivative of the outside as according to the product rule, and then you take the derivative of the inside in a couple of steps. Okay, so now moving on from there, r dot I is equal to r b dot. Since this is a vector of constants, it's going to be equal to 0, plus it dot b times 3 0 0. So you're basically multiplying this matrix by this vector 3 0 0, and when you do that you will end up with a vector 6q naught dot minus 6q3 q3 dot, then 6q naught dot q3 plus 6q naught q3 dot 0. Now, if you have watched my previous videos for this particular problem, where I've used basically vector multiplication and differentiation of vectors, what you always end up with is some set of trig functions down here. And trig functions are a nonlinear function, well, are nonlinear functions. So when you put them into a graph or something, you end up with something like this. If you're ever developing a control system or something, you'll have it get big and get smaller, or it will oscillate forever, or whatever it is. When you work with quaternions, you have a linear system. So it's much easier to work with and control a line than it is a constantly changing line like this. And this is what the quaternions allow you to do, is create a linear system to solve from and take differentiations from and everything else. So quaternions allow you to create something that's much more manipulable and controllable if you ever extend beyond any of this work. So once you find the velocity of something and you then want to create a controller for it or something, quaternions are just a lot handier for that. So this is a different form from the other problems because it's in quaternions. There's no way to really transfer the other solutions that are in trig functions into a quaternion form that I know of right now at this point, but quaternions are just kind of nice because they set up a linear system. Some people are confused by them because they have the 4 sets, but really all you have to do is set up where you're rotating, how much you're rotating around that particular spot, and then take the quaternion matrix, turn it into Euler angles so that you have a transference from the information that you have into quaternions, and then you use the quaternion matrix again to get ITB, and then go through and solve it. Got to remember a little bit about quaternions. You don't really treat them as variables, you treat them as functions, and then you go through and you get a nice vector at the end that's pretty handy to use. And that's how you find the velocity of a point in a manipulator, by using quaternions. That'll be the last example that I use for this particular problem.